So hi to everyone that's joined. We'll just give it a minute or two for folks to come in, and then start a couple minutes past the hour. And just to note, we're live streaming as well to YouTube, so you can catch up afterwards. Great. So I think let's get going, and I think people probably kind of still keep coming in. So just to get going with the introduction, thanks everyone for joining us today for the Next Rocky Worlds discussion. Just as a reminder, these are happening the first Thursday of every month. We've got a series of talks coming up and a series of talks gone by, all of which you can see on YouTube as well, if you want to go back and see what's happened before. But today I'm really excited. So we've got Satoshi Okuzumi from Tokyo Tech joining us to speak about the migration of the snowline and protoplanetary disks. I think it's a really fantastic topic for Rocky World discussions because of how central the incorporation of volatile elements, carbon, hydrogen, and so on into rocky planets is for their habitability, and more broadly for their chemical and physical evolution. So I'm really excited to see this topic kind of touching on this key episode in planet formation. Just as a touch on the kind of logistics for the next hour. Obviously you've got the introduction, then a sort of 30 to 40 minute talk with then time at the end for discussion. We'll be able to take questions just by raising a hand, and hopefully you can jump on camera to ask the question, or you can pop it in the chat, and then we'll close and we'll be done by the end of the hour. Just as a bit of etiquette, please use your full name. We'd really appreciate knowing who everyone is to kind of sort of keep the community aware of each other. That would be great. And please keep muted through the talk. And yeah, it would be great to see you on video when asking a question kind of later on. I think that's everything from me. So I'll stop sharing screen and hand over to Satoshi.
Yes. Okay, so can you see my slide?
Yeah, can see those. Great.
Great. Okay, so thanks for the introduction. Hello everyone. My name is Satoshi Okuzumi from Tokyo Tech, and I'm an astrophysicist working on the planet formation and also the evolution of the snowline. And today I'm very excited to be able to discuss with you about the origin of rocky worlds. And today I'd like to present our recent work on the modeling of the evolution of the snowline in protoplanet disks. The snowline is the location where water ice sublimates, and its location is very important when you think about the chemical composition of planets and the chemical diversity of planets. And today I will show you the results of our recent magnetic hydrodynamical disk evolution model that suggests that protoplanetary disks might be colder than generally believed, and the snowline can be closer to the central star because according to the MHD simulations, the internal heating of the disks is very inefficient. Okay, so let's get started. Okay, so the reason why we want to understand the thermal structure of the disk and also the location of the snowline is, of course, we want to understand where rocky planets like our own form. And for example, so if you take the Earth, for example, we know that the Earth only contains a very small amount of water. For example, the ocean comprises only 0.023% by mass of the Earth's mass. And it is generally believed that early Earth only also contained less than 1% water, 1% water. So they are, so we can say that the Earth was born very dry, and the Earth is very different from other solid bodies in the outer part of the solar system. For example, C-type asteroids and comets contain much more water, so they are very different. So the fundamental question here is when, where, and how do these dry planets form? So this is the question we want to understand. Okay, so in order to answer this question, we definitely need to understand the location of the snowline. And under the typical pressure conditions of the disks, the snowline is generally located at a position where the temperature is about 150 and 170 Kelvin. And inside of the snowline, we believe that there are silicate particles without a lot of water, and these silicate particles would grow into rocky planetesimals. And outside of the snowline, there should be icy particles, and these icy particles would grow into icy planetesimals like C-type asteroids and comets. Okay, so the snowline determines the which kind of planets form in a different part of the disk. Okay, and of course, it is possible that icy planetesimals that form very early can evolve into rocky planetesimals due to dehydration caused by the radiogenic heating. But in any case, it is likely that the snowline affects the location where rocky planets form. So this is why we want to understand the location, or we are interested in the location of the snowline. Okay, so when we ask where the snowline is, so it means we are asking about the position, not the temperature of the snowline in the disk. And in order to answer where the snowline is, the position of the snowline, we need to understand the thermal temperature distribution of the disks. And in order to understand this, we need to know the heating processes that operate in the disks. And there are two important heating processes, and one is the stereo heating, stereo radiation heating. And this is you always have this heating process, but the problem is that this heating process cannot efficiently heat the interior of the disk when the disk is very dusty. For example, if you have a lot of dust particles in the disks, then those dust particles would block the stellar light that would otherwise penetrate down to the midframe. But if you have a lot of dust particles, they cannot heat efficiently the midplane region of the disks. Okay, so this means that if you only have this process, then it is we can expect that the disks should be very cold. However, it is possible that there are other internal heating processes induced by disk dynamics. For example, if you have a turbulence, then turbulence can produce internal heating when they dissipate. And also, if you have an electric current associated with the MHD processes of the disks, then this electric current can produce Joule heat when they dissipate. So these processes can be important, particularly when the disk is very optically thick, meaning that if the disk has a lot of dust particles, because if these internal processes, heating processes happen deep inside the disks, then the heat cannot escape easily. So these processes can strongly contribute to the internal heating, the heating of the midplane of the disk. Okay, so it is very important to understand which kind of internal heating processes happen in realistic protoplanet disks. Okay, so this is what we are working on. And this is, I'm just showing you two examples showing how important the internal heating processes is. So this is the example where we calculate the location of the snow lines, not only the H2O snow line, but also the snow lines of ammonia and CO2 and CO. And here I assume the dusty disk around our solar mass young star. And this is the age of the star. And this is the distance from the central star. And as you can see, the water snow line is always outside of the 1AU region, 1AU orbit, the current Earth's orbit, thanks to the efficient internal heating. Before that, in this case shows you the case where you have stellar radiation and also the uniform internal heating. Okay, so in this case, thanks to the internal heating, the inner part of the disk is very warm, so that the snow line is pushed outside of the 1AU orbit. So in this case, you can easily assume that rocky planets can form around this 1AU orbit. However, if you switch off the internal heating, so something different happens. In this case, you don't have efficient internal heating around 1AU orbit, so that the H2O, so what you see here is that the H2O snow line crosses the 1AU orbit and migrate inward of the 1AU region within the very early stage of the planet formation. So this is 1 mega year. And it is usually believed that the planet formation happens on the time scale of about 1 mega year. So this figure shows you that if you don't have any internal heating source in the disks, it is likely that the H2O snow line is located at the region inside of the current Earth's orbit. Okay, so in this case, it is very easy. It is not easy to answer whether rocky planets can form easily around this orbit. Okay, so this example shows you how the internal heating process is important. And this is just to show you what would happen if the mass of the central star is 10 times smaller. So this is the case for M-type stars. And in this case, the same happens. So if you don't have internal heating, in that case, the H2O snow line can lie inside of the 0.1 AU orbit, so very close to the central star. Okay, so we need a good model for that describes the disk dynamics in order to predict the location of the snow line. Good. So here I'm showing you two popular models of the dynamics of protoplanet disks, especially the accretion of protoplanet disks. And left panel shows you the classic viscosity-driven accretion model. So this is also called the turbulence-driven accretion model. So this model assumes that there's turbulence everywhere in the disks. And this turbulence acts as a viscosity, and this transfers angular momentum outward, and that causes the accretion of the gas onto the central star. So this is a classic model of accretion disk. And the problem with this model is that we actually don't know whether there's strong turbulence in the realistic disks. There's no strong observational support for the presence of strong turbulence in the disks. And also, according to theory, we don't expect that there's strong turbulence in the very inner part of the disks. Yes, so this is a problem with this classic model. And the more recent popular model is what we call magnetically or MHD-driven accretion model. So in this scenario, we assume there's a magnetic field threading the disk, and this magnetic field produces the wind. So this is called MHD-driven wind. And at the same time, so because this wind not only takes away the mass of the disk, but also takes away the angular momentum of the disk. So as a back reaction of this wind, there's an accretion of the gas within the disk, because this gas loses angular momentum because this wind takes away the angular momentum. So that's why in this case, even in this case, accretion happens in the disks. And we don't, in this scenario, we don't necessarily have a turbulence in the disk. Okay, so we only have accretion caused by the wind. Okay, and this scenario is predicted from recent MHD simulations that takes into account the realistic disk ionization structure. And this is one example. So this is the two-dimensional global MHD simulation done by Training by in 2017. So this shows you the two-dimensional structure of the disk. So this is the midplane, and this is the height above the midplane, and this is the distance from the central star. And this plot shows you the radial mass flux of the gas in the disk. Okay. And this calculation takes into account the realistic ionization structure of the disk. So, and ionization of the gas is relevant here because only plasmas can interact with the magnetic field. So you need to know where you have plasmas in the disks. Okay, so that's why you need to take into account the ionization structure of the disks. And if you take into account the realistic ionization structure of the disks, what you find is that the accretion happens in the disks. But what is interesting here is that the accretion only happens on the surface of the disks. So this is the vertical. This shows you the vertical distribution of the radial flux at 10 AU orbit. And this negative value shows the accretion flow, inward accretion, inward radial mass flux. As you can see, you have a strong surface accretion, and the location of this accretion flow is about 4 scale heights below the midplane. So HD is the disk scale height. This is the typical size of the thickness, vertical thickness of the disks. Okay, and you don't have a strong accretion flow at the midplane in this case. Okay. So why we only have surface accretion flow in this scenario? So in order to understand this, I'm showing the cartoon showing the ionization structure of the disks. So because the protoplanetary disks are very cold, you cannot expect the thermal ionization in the disks. You only expect that the disk is ionized by high energy sources like stellar UV and X-rays. But these X-rays and UVs can only penetrate on the surface of the disks. So you only have a partially ionized layer only on the surface. And at the midplane, you only have almost neutral gas. And this gas cannot interact with the magnetic field, okay, because you don't have a plasmas. So no electric field, no electric current in this midplane. So this is the reason why the accretion flow only happens on the surface of the disks. So only this partially ionized gas on the surface of the disk can interact with the magnetic field and loses angular momentum and causes the accretion of the gas. Okay, so this is why the accretion happens on the surface of the disk. And this is very important when you think about the heating of the disk, because this would mean that the heating of the disk only happens on the surface of the disk, and nothing heating process can operate around the midplane in this scenario. So this is very different from what we expected from a viscous accretion model, where people usually assume that the turbulence is everywhere and accretion heating is released not only the surface but also at the midplane. So this is very different. So what will be the consequence of this surface accretion flow on the temperature of the disk? So in order to answer this question, we have conducted MHD simulations where we calculate the vertical structure of MHD accretion disk by taking into account the ionization structure of the disks. We calculate the ionization degree of the disk at different heights of the disk, and calculate the Joule heating rate. So in the framework of magnetic hydrodynamics, the heating happens through the Joule heating. Okay, so in this calculation, we investigated the vertical distribution of the Joule heating rate by using this calculation, and this is what we get. So this shows you the vertical distribution of the heating region, and this orange region is where you have a strong current layer, and what we found is actually the Joule heating is narrowly concentrated on this region, and this region corresponds to the region where we have seen the strong accretion flow in the previous slide. Okay, so this is about 4 scale heights above and below the midplane. Okay, and as we expected, we don't have any strong Joule heating at the midplane, simply because you don't have ionization at the midplane. There's no plasmas at the midplane, so the midplane cannot sustain electric current. So this is why you don't have Joule heating at the midplane. You only have the Joule heating on the surface of the disk. Okay, and this is very important because this would suggest that the midplane is likely to be cold because these Joule heating layers cannot efficiently heat the midplane layer. Okay, so we have modeled our MHD simulation, the results of our MHD simulations, and we have made a toy model in which we calculate the the location of the heating layer from ionization calculations and compute the midplane temperature by using the location of the current layer. So this can be done easily by analytical calculations. So with this model, we are able to calculate the long-term evolution of the midplane temperature with time without using MHD simulations. Okay, and this is what we get. So this again shows you the location of the sunlight. So where the temperature is about 160 kelvins, and this is the stellar age. And in this calculation, we take into account the accretion heating and also stellar radiation heating. And so this is what you would get from the standard classic viscous accretion model. And as I mentioned, in this scenario, you have efficient internal heating at around 1 AU orbit. And in this case, the snowline is far away. The snowline is outside of the 1 AU region within 10 million years after the birth of the central star. However, our MHD model, based on our MHD simulations, show that because you don't have a heating process at the midplane, the midplane temperature is very close to the temperature in radiation-only protoplanet disks. Okay, and in this case, as I mentioned, the snowline crosses the 1 AU orbit in a very early stage of planet formation, within the 1 mega year after the formation of the central star. And after that, the snowline is lies inside of the current Earth's orbit. So this is our conclusion. So our magnetically accretion disk models predict that the disks are actually very colder than previously expected, and the snowline crosses. So our model predicts that the snowline crosses 1 AU within the 1 megayear in the very early stage of planet formation. There's one caveat, because actually this model assumes that the dust particles size. So in this case, in this calculation, we assume that the dust particles are 0.1 micron in radius. So these are very small particles. But what we found is that the location of the snowline in our MHD model depends on the size of dust grains, because small dust grains affects the ionization structure of the disk. So if you have less small particles, then you have a higher ionization, because small dust particles can efficiently accrete plasmas. So if you have a lot of dust particles, small dust particles, then the ionization decreases, and you have less ionization. You have less Joule heating. But the opposite happens if you have less dust particles. So meaning that the location of the snowline in this MHD model depends on the amount of small dust grains that can be easily charged. Okay, and we are working on we are now currently working on modeling the effect, take into account the effect of dust growth in our model. And stay tuned. And but our tentative conclusion is that the MHD model, MHD protoplanetary disk should be much colder than the standard viscous accretion model, because the absence of heating process at the midplane. Okay, so here's a summary. So we have shown that astrophysical simulations predict that magnetically MHD accretion disk model can be very cold, much colder than expected from the classic viscous accretion model. And in the extreme case, the snowline and the solar nebula may have been migrated to less than 1 AU orbits within the first 1 mega year of planet formation. So we want to understand what would be the consequence of this very early migration of the snowline. And the problem is simple. So we expect that solid bodies that form outside of the snowline would contain a lot of water, at least initially. And the water content is not consistent with the amount of water in the current Earth. So the question is how we can explain the formation of the Earth and other terrestrial solar system planets in the disk, despite that the snowline was located inside of the snowline. So I want to raise two questions to the audience. So let's assume that our theory is correct. And let's assume that in the solar nebula, the snowline was located inside of the 1 AU in the very early stage of planet formation. Then how we can explain the formation of solar system rocky terrestrial planets? And the second question is, assuming that our theory is correct, can we still expect that most habitable zone planets are rocky, or should we expect there must be a number of water worlds in the habitable zone? And what would be the consequence of this? Okay, and so let me give me so I will use the final 2 minutes to explain more about the two questions. And as for the first question, I can show you several possibilities where solar system rocky planets can form. For example, one example is actually rocky planets in the solar system formed very close to the central star, inside of the 1U orbit, and migrated afterward. For example, some simulations show that the rocky planets can migrate outward when the gas disk is dissipated. And this is one possibility. And another possibility is that if you have a Jupiter in a very early stage of solar system formation, then Jupiter might block the icy pebbles that would otherwise drift into the inner region of the disk. And so in this scenario, Jupiter's core can prevent the icy particles from entering in the inner disk regions and are accreted by the rocky planets. So this is another possibility. And I think it is also possible that actually rocky planets in the solar system formed from dehydrated icy planetesimals that formed very early. So if icy planetesimals form very early, then they can dehydrate by the action of radioactive heating. I think this is possible. So yeah, so what do you think? So what is your favorite scenario? And do you have any? If you have any other good ideas, so please let me know. And the second question is: are habitable zone exoplanets really lucky? So this figure shows you the location of habitable zone planets as a function of the stellar mass. And it is very known that according to the classic theory of the snowline is located outside of the habitable zone. And in this case, you don't worry about the composition of habitable zone planets. So you can expect that habitable zone planets should be rocky unless planets migrate inward. However, according to the scenario where the snowline is the disk is very cold, so for example, if you use the radiation, if you use the disk model where you only have stellar radiation, if you don't have internal heating, then the snowline in this kind of cold protoplanet disks should lie around here. So this shows that the snowline in this model overlaps the location of the habitable zone. And this would mean that some of the planets formed in the present-day habitable zone may have been actually initially water-rich. And the question is, so what would be the consequence? So would these water-rich planets would evolve into water worlds in this region? And so if it is the case, would these water-rich planets would host life on such planets, despite that these water-rich planets would likely have a thick ocean in addition to high-pressure ice? So it is possible to imagine that these water worlds can have life on the surface. So this is my question to you. Okay, so I will stop here. So thank you for your thank you for your thank you for asking, and I'm happy to take your questions.
Great, thank you very much, Satoshi, especially for the two kind of provocative questions at the end. So yeah, it'd be great to hear any questions or thoughts from people at this point. Just as a reminder, you can raise your hand, raise your Zoom hand, and if you're able to jump on camera and ask your question, I'll invite you to come forward, or you could drop it in the chat and I can sort of ask the question on your behalf. Sean, yeah, you've got your hand up. Go on, please jump forward.
Hello. Can you hear me all right?
Yes, perfect.
Excellent. Thank you for the great talk, Satoshi. So since this mechanism for heating that you're talking about, this magnetodynamic mechanism, occurs on the surface of disks, is there any observational potential to observe that with radio observations, or are there kinds of means in protoplanetary disks that we see out there?
Some people are working on that direction. Some people say that there might be there's some observation that shows that there can be a disk wind from the surface of the disk, but I'm not sure if this is actually driven by MHD, the magnetic field. But in any case, there's an observation that shows the wind. But I don't know if there's an evidence for the presence of surface accretion, like like predicted from MHD models. But I think the observers are trying to find the evidence of the surface accretion by using ALMA, for example.
Cool. Thanks for that question, Sean. There's a question in the chat from Sasha Boone. This is a question about timescales. So it's an interesting one. How long does it take for the volatiles to leave from inside the snow line? So I suppose, yeah, if the snow line's moving over a particle with water ice on it, what's the timescale for it losing that water, or vice versa, I suppose, the water going back onto a particle?
Yes, so it depends definitely on the size of the screens. If you think about, for example, icy pebbles, centimeter or millimeter size, then they would instantaneously lose their water as soon as they enter inside of the snow line. So this is instantaneous. Yeah. But I think the time scale should be longer if the particles are much larger. So it really depends on the size of the particles that contain ice.
Yeah, so you think if you could put water ice in tens of meter sized objects, then that's potentially armored from loss, do you think?
Yeah,
so
I think so. Yeah.
And I guess objects of that size wouldn't yet be big enough for radioactive heating to drive water loss. So sort of maybe a potential reservoir of water inside of the ice line. That touches on something I was wondering about myself, which is to what extent are your models moving particles around, which I guess is this question of to what extent are those boundaries blurred, the snow lines in practice blurred by the radial drift of particles, in particular ones large enough to retain a bit of water for some time after crossing the nominal water ice line.
Yeah, we are currently working on that, and yes, and yeah, but the problem is, according to recent ALMA observations, the growth of dust particles is likely to be regulated by fragmentation, a collisional fragmentation of dust particles. And usually, the observation shows that the maximum size of dust particles is about it can be less than 1 millimeter. It can be as small as 100 microns. And there are a lot of observations that suggest that. And in that case, we do not expect that the solids in the disk can retain a lot of water when they pass the snow line. But we don't know much about the size of dust particles at 1 AU region. So usually, ALMA observations are looking at for example, 10 AU or 100 AU regions. So dust particles inside of around 1 AU region might be much larger. Yeah, and also it is definitely true that planetesimals should form in any case. And so if the planetesimals contain a lot of water, and if these planetesimals drift in a disk, they might transport the water in a disk across the snow line.
Yeah, that makes complete sense. So the size distribution of particles in the disk and the size distribution, I suppose, of particles building rocky planets ends up being key for understanding how wet a rocky planet may or may not be. There's another question in the chat, and I apologize if I mispronounced the name here, from Baipav Srivastava. And yes, it's in that plot where you showed the MHD results for the radial mass flux, and there was an asymmetry about the midplane of that plot.
Okay.
Why?
Okay, let me try to explain the asymmetry. Okay, so before that, so actually I didn't mention, but actually there's a set of inward flow and outward flow around the just above and below the midplane. But this inward flow and outward flow cancels out, and you are left with this surface accretion. But interesting here is you only have this accretion flow below the midplane and not above the midplane. And but actually, this result depends sensitively on the ionization structure of the disk. And to be honest, I don't know the condition where you have accretion flow on one side of the disk and not in the other side of the disk. And actually, other simulations show that two accretion flow, more symmetric flow above and below the midplane. So I think there must be a condition where you have asymmetric accretion flow, but the condition is not yet understood, if I understand correctly.
And it's not a result of an initial condition that's sort of baked in.
Yeah, you always have this configuration under the certain ionization degree. The one reason is that so for magnetic field, so if you are a magnetic field, you don't want to bend many times, and in this configuration you only have a bend at one point, and this is energetically more stable. And this is one possible explanation, but I'm not sure if it is correct. Sorry, this is very complicated.
Yeah, that was a kind of enigmatic feature of the yeah, brilliant. Any more questions or thoughts from people? Question from Hannah in the chat. Hannah Sanderson: how sensitive are your results to the stellar magnetic field strength and structure, and will this change the results if you move to strongly magnetized stars, such as rapidly spinning, rapidly rotating M dwarfs? And is temporal evolution of the field important?
Okay, thanks for asking that. So, because I didn't mention the origin of this B field. And actually, the origin of this B field is not the stellar B field, but the magnetic field inherited from the parent molecular clouds. So these magnetic fields are connected to the molecular cloud around the disk. The reason is the magnetic field of the central star decays very quickly, because the magnetic B field goes as the distance of the central star to -3, -2 in the case of the dipole. Okay, so you have negligible contribution of the stellar magnetic field around, for example, 1A region. Of course, the stellar magnetic field is important in the vicinity or the inner edge of the disk, but you can ignore the contribution of the B field, a stellar B field around 1AU.
Brilliant, thank you. So Tim's put a comment in the chat to provoke more thought or questions. As to a recent paper which has the result that the ordinary chondrites accreted water rich, the inference being they accreted beyond the snow line. And should we then be thinking that the accretion history of the inner solar system should be rewritten to suggest that it took place outside of the snow line for some time rather than inside of the snow line? And I suppose this is maybe I suppose this is also touching on maybe what ends up being a dichotomy between the apparent wetness of the assembled rocky planets, and what we might imagine were their constituent parts, the chondrites, and how to understand that dichotomy. I mean, I have one thought on that, which is timing. I mean, I suppose your models themselves emphasize how important timing was for everything, with the significant movement of the snow line, and even in the irradiated, or the MHD heated case, the inner solar system was inside the snow line very early on, right? In those models, certainly for like a G-type star, maybe not for an M-type star. With the result being that if you grew I suppose the result of that is if you grew your rocky planets within 1 million years, maybe within a few 100,000 years, then they would be forming dry. And then if the meteoritic record is a later or a younger archive, then they would form wet. Is that one possibility? Are we just now needing to make our rocky planets very quickly in the context of the solar system's history, at least?
Yeah, I think that's one idea, but there's one problem, which is unless you block the icy pebbles coming from the outer part of the disk to the inner part of the disk, these icy particles will eventually enter the 1A region, and some of the icy pebbles might be accreted by these rocky planets that form early at 1A region. So this means that even if you make rocky planets at 1A region during while the solar nebula was hot, you have to stop the inflow of icy pebbles. So this is why so this scenario suggests for example, if you have a Jupiter's core, then this Jupiter core should block the inflow of the water pebble, icy pebble. And I think this so some people expect that this scenario is consistent with, for example, the isotopic dichotomy of the solar nebula, but I don't know.
Yeah.
My feeling is that even if you have our gas giant core, some of the icy pebbles should go to the inside of the snow line, because they are not only pebble-sized dust particles, but also very small icy particles. And small icy particles can move across the gap. So these particles can deliver some amount of water to the inner region. And this might be good for explaining the origin of ocean. I don't know.
Yeah, that makes sense. Yeah, so invoking Jupiter to do a lot of work, or proto-Jupiter to do a lot of work for us. Which is interesting in the context of what it takes to make a habitable or rocky or Earth-like planet. Does it need an outer giant companion? And that'll be fascinating to test that in the years to come. See whether there's any systematic relationships between water poor worlds and outer giant companions. Cool. Any more thoughts or questions? It's been interesting discussions so far. Thanks everyone who's contributed. Great, thank you, Hannah, for that, for an additional link to a paper there. I should also point out that the Discord server for Rocky Worlds discussion is another place to share papers and thoughts. So we could post these links in there actually after the meeting today. And if you're not on the Discord server, I think probably it's linked to from the Rocky World discussion website. I think if Tim's listening, he can confirm in the chat. I think that probably is. Cool. We've got another question from Sean. Yeah, do jump back in, please.
Yeah, sure. Thank you. So in your models, do you do anything with the timing of the gas dissipation? I mean, some of the models looked like they were going out to 10 million years or so. And my understanding is that the gas dissipates from the disk, and for some stars in less than that time scale, or typically shorter than that time scale. So am I right in thinking that? And do you address that at all in what you study?
So your question is about the dissipation of the disk.
Yes. So the MHD mechanism depends on there being gas, and if the gas dissipates, in 6 million years or 5 million years instead of 10, would that matter? Would that change? I guess that wouldn't, if you're not growing planets yet in the results that you're presenting. I guess that wouldn't really affect necessarily what's going on. Just how far inward the snow line would be able to move by this mechanism. So sorry for the mixed up question. Thinking out loud.
Okay.
Sorry about that.
Okay, so yeah, so if so actually the dissipation of the disk is important in this context, because if the gas is dissipated, then the small particles would not enter into, for example, so let's think the situation where this disk wind takes away the gas in the inner region, and in that case you have a gas gap in this region, gas cavity in this region. And in that case, dust particles can no longer enter the inner region. And what is good with this is that you no longer have small dust particles in these regions. And if you don't have small dust particles, then you don't have any particles that block the direct solar radiation. So in that case, you can directly receive the stellar radiation in this region, and the temperature goes up. Temperature goes up in that case. Okay, so this calculation assumes that there's a lot of gas and there's a lot of dust, and those material block the stellar radiation. But once the gas is gone, actually the snow line actually moves outward. Yes. And if you already have, for example, planetesimals in that gas dissipated region, then they might manage to grow into rocky planets. Yes, and actually you don't need the gas to explain the formation of the rocky planets, because the rocky planets doesn't have a lot of gas. Yes, I think so I mean the dissipation of the gas changes the timing of the snow line migration, and actually the reverse the direction of the migration when the gas is dissipated. So I'm not sure if this is answering your question, but yeah, I mean,
no, it's an interesting point to consider.
Very important. Yeah.
Right. I mean, if you just need a little bit of water to your rocky planets, you could have this mechanism operate. The snow line moves inward, and then the gas dissipates. And if that changes with stellar mass, then you might get some different balance of rocky worlds versus just a little bit of water worlds, and then so forth. Interesting.
Yeah.
Yes, there's another key time scale of the lifetime of the disk. It's when you form your planet, and how long the disk lasts. Yeah, connecting then to the protoplanetary disk folks and their observational kind of summaries of disk lifetimes as a function of stellar mass and other kind of external parameters, the environment of the disk and so on. Cool, that's a really good connection to have made. Cool. Well, I didn't see any other hands up. Thanks everyone for the thoughts. I think Sasha's shared a digestible link to the Discord server, and I've shared a completely indigestible one, which may even not work, judging from how horrible it looks. If you're not part of the Discord server, please do join. We've dropped links to the papers discussed in there, and I think Tim's added one other. So it's been a really interesting discussion. I think thank you so much, Satoshi, for giving us so much to think about touching on so many topics. Really appreciate that, and for participating in a really rich discussion. Just a reminder for everyone, talks are continuing. The next talk is going to be 7th of September. We're going to hear from Anjali Piet from Carnegie, our rocky planet or water world, the observability of low density lava world atmospheres. That's going to be the next talk. And this talk and all previous ones are have been live streamed and recorded on YouTube to look back at if you want to check out any of those. So thanks again, Satoshi. Thank you everyone for joining and participating. It's been really fun. Hopefully see you all in a month's time. Take care, everyone. Bye.